Okay, let's talk about integer exponents. As this first bullet says, integer exponents are used to denote repeated multiplications. Some applications are in population. For example, let's say you start out with 300 individuals. So this is an example. And I don't mean people, it could be rabbits or something like that. And every quarter of a year, so every 3 months, the population doubles. So you multiply by 2 to get the new population after 3 months. After 6 months, you multiply by 2 again. After 9 months, multiply by 2, and so forth. So let's say you do this for 4 years. How many rabbits, assuming they have enough space and food? So you have to multiply this, 4 years. Eventually, there's a last 2. So 4 years. But this there's 4 of those in each one of the years. So actually, that is equal to 16 times. It can get really complicated once you start getting a lot of those same factors over and over again. So that's why we use um, exponents, and this happens frequently. Um, Instead of doing 2 times 2 and then explaining how much it is, you just do 2 to the 16. So the exponent is a smaller font number or expression on the upper right corner of the number. By the way, whenever you're using an exponent, um, this guy is called the base, and this guy is called the exponent. And sometimes um, when we don't have enough room, we put this as 2 hat. This is a symbol on the keyboard, and 16. That means that this is the exponent of the 2. So that is sometimes what we do. Also, so this is one example. It's called this example 1. Example 2. Let's say you are borrowing $1,000, or you're putting $1,000 in the bank. Same thing, and they're paying you 2% per year. So that means we have to multiply by 1 for the $1,000 and then 0.02 for the 2% per year. And you want to know what happens after 10 years. So technically speaking, you would have to multiply 1.02 with 1.02 with 1.02, for 10 times 1.02. If the bank pays you 2% every year, and if you leave your money for 10 years, instead of doing that, you can rewrite this. And again, you have to explain, well, there's 10 of them, 10 of them, which can get um, difficult to write. So you just write 1,000 and then times 1.02 to the 10. Again, there is the base and there's the exponent. So that represents a multiplication of 1.02 times 1.02 times 1.02 10 times, 10 of those. And the same thing happens with decay. So let's say you take a medication. So this is example 3. And I don't know, you take 10 milligrams of a medication, and then your blood, no, your organs can get rid of the medication because it enters into your blood system, and maybe your kidneys and some other organs get rid of half of it per hour. So after 1 hour, you only have half of it. After another hour, you may have half of it. And after another hour, you may have half of it. So one question somebody could ask is, well, what if you do this? Uh, how many milligrams are going to be in your system, in your blood system, after say 12 hours, 12 hours, or 12 times? So instead of writing this in this cumbersome way, we just write, well, 10 times. So this is the multiplication, 1/2, and the quantity 1/2 has to be raised to the 12th power. So that means we're going to multiply 1/2 times 12 times 12. No, sorry, I said it wrong. 1/2 times 1/2 times 1/2 times 1/2, 12 times. And then after we get that product, we can multiply with 10. Alternatively, you can multiply 10 times a half, in which case you get 5, and then times a half, 2.5 times a half, 1.25, and so forth until you finish all the halves that you got to multiply by. Yeah. By the associative property, you can do all the halves together and then multiply once by 10, or you can multiply the 10 still once times the first half, and then that answer times a half, that answer times a half, and so forth. Yeah. Typically, we do this first and then multiply by 10 only once after we multiply the 1/2s together. So this has a lot of applications. These are just a few of the applications that I thought of the top of my head, but I'm sure there's plenty applications for exponents. So let's look at some numbers. If you have a base with an exponent of 4, of course, that means a times a times a times a. So it is a repeated multiplication of a with itself 4 times together, all together. A cubed means, of course, a times a times a. A squared is a times a. A to the 1 is just a. And whenever we're writing an answer, we never keep the a to the 1. We always simplify down to a. We never, in a final answer, we never write down the 1 when we have an exponent of 1. Let me write that down. In a final simplified answer, we do not write the 1 as an exponent. All right, and then a to the 0. Before I finish this table, let me do a table of numbers, because that will make a little more sense if we look at the numbers. So example 5, let's say you have 2 to the 4. So that is 2 times 2 times 2 times 2, and that is 16. 2 cubed is 2 times 2 times 2, which is 8. 2 squared, 2 times 2, 4. 2 to the 1, 2. Now, let's analyze what's going on here. Every output, as we move from one line to the next line, is being halved. From 16, half of that is 8. Half of that is 4. Half of the 4 is 2. Half of the 2 is 1. So if we continue with this sequence, and mathematics works very nicely with patterns. So if we continue with the same pattern, we got 2 to the 0 is equal to 1, which is true. That 0 means, in this context, absence of factors. No factors means 1. 2 to the negative 1. Okay, now let's think about this. We've been halving each one of the outputs. Half of 16, 8. Half of 8, 4. Half of 4, 2. Half of 2, 1. Half of 1, 1/2. Aha. So 2 to the negative 1 is 1/2. 2 to the negative 2. Well, what is half of a half? A fourth. Think about it. Split a half, you get a fourth. 2 to the negative 3 is 1/8. So when we have a negative number, we're really working with the reciprocal of the output we would have had otherwise. So 2 squared is 4, but because we have a negative, we're doing the reciprocal of that. And that rule always applies. Whenever we have a negative exponent, we're really doing the negative, rather, the reciprocal. So 2 to the negative 4 is going to be a 1 over 16, and so forth. So now we can finish this after we saw that example. A to the 0 is 1. Oh, there's one rule about this, or one requirement. As long as A is not equal to 0. Because 0 to the 0 we cannot do. But so in this case, we're assuming that A is not 0, and any number to the 0 is automatically 1, as long as that number is not equal to 0. Otherwise, we don't know what it is. It is undefined, I suppose, as some people would say. A to the negative 1 is 1 over a to the negative 2 is 1 over a squared, a to the negative 3 is 1 over a cubed, and so forth. All right. So things get more complicated. Let's split this page into vertically, 6. It gets more complicated if we have, let's say, 3 over a to the negative 2. Let's think about this for a moment. All right, so this is 3 over, and a to the negative 2, as we have said earlier in example 4, is 1 over a squared. So how do we simplify? By the way, oftentimes when we have negative exponents, the way we simplify that is by getting rid of the negatives. So this is really 1 over a squared. Now, whenever we have a fraction and there are 3 pieces to it, or 2 fractions rather, it is important to know which one is the denominator or numerator of each one of the fractions. I'll elaborate on that in a moment, but let's finish this up. So this is 3 divided by this fraction. All of us know, and if we didn't know now, let's recall that when we divide by a fraction, we multiply by the reciprocal of the denominator, or reciprocal of the fraction we're dividing by. So the reciprocal of 1 over a squared is a squared over 1. So that is simply 3a squared. So 3 over a to the negative 2 is the same thing as 3 squared. I guess a simpler rule is to say, if you have a negative exponent in the denominator, just put that expression on the other side of the fraction line with a positive exponent, and vice versa. If you have, say, example 7, 3a to the negative 2 over b, this is the same thing. If we go through the same process, very quickly we realize that this is the same thing as moving this expression down here. So keep the 3 on the numerator, keep the b in the denominator, and then just put the a on the other side of the fraction line, but with the opposite exponent. So we can change the sign of the exponent as we move either from the numerator to the denominator or from the denominator to the numerator, as long as we are multiplying. If we're adding or subtracting, then that doesn't work anymore. We have to do something else. So we gotta just keep an eye on the fact that we are either multiplying or dividing. And that's the way we handle negative exponents. A rule is that the exponent is attached to only one of the factors. So this is a rule. The exponent is attached to only one and exactly one item. Okay, so be very, very careful when you are working with exponents. So if you have, as an example, let me keep track of my example. So next example would be example 8. That way, when you're talking about this about the videos, you can refer back to the example. So if you have ab squared, how many b's are there? How many a's are there? This is exactly 1a and 2 b's, because the 2 is attached to the b, not to the quantity ab. Compare that to ab quantity squared. That really means ab times ab. So we actually have 2 a's and 2 b's. And that means that we have actually a squared, b squared. This is one of the properties of exponents. Please review properties of exponents they are in just about any book, any algebra book. You can see properties of exponents. I'm not going to copy them down here on this video. Instead, I'm just going to ask you to please check out any algebra book, and they will have a bunch of properties of exponents. This is one of them. You don't have to go through this step. I just want to emphasize that the 2 attaches to the 2 of them because of the parenthesis. So the parenthesis unifies this as a single quantity. Here, there's no parenthesis around AB. So the 2 is only attached to the B, not to the quantity AB. So there is a big difference here. That difference is even more noticeable when we have a negative. So negative 5 squared versus negative 5 quantity squared. Okay, let's start with this one. Negative 5 squared quantity squared is really negative 5 times negative 5. And so we have two negatives multiplying together, and the final answer is 25. That is not the case here. And it is quite tricky. It is kind of almost, it's not very obvious to see that this is not the same. Think of this as negative 1 times 5 squared. So the 2 is actually attached to the 5, not to the negative 1. If this doesn't seem correct to you, please fix it in your mind, because this is the way all of the math people think of when they see a negative quantity or a number, say 5 squared. We think of a single negative, not two negatives, as in this case. So what I was trying to say is, if you think of this as that, change the way of seeing it. It isn't necessarily that you were wrong. It's just that you didn't know that this is what's going on. That's the way most of us see it. So this is a little bit conventional. What I mean by that, if nobody tells you, you may not know how to handle this situation. Anyway, so this is actually negative 25. And this, confusing this with this, is a big deal in algebra. Some students may say, hey, all I missed was a negative. Yes and no. A negative is a big deal, but there's more to that. We are, in this kind of question, we are testing exactly whether you do know or do not know how to handle this situation. So that's why oftentimes in a simple problem like this, we may lose a lot of the points of the problem, because that's precisely what the problem is about, to test whether we know how to handle the situation. So please be very, very careful with especially with negatives and exponents. Yeah. Some students make the mistake without writing it, or the other way around, write it the wrong way, and then at the end they end up with a correct answer. So writing it incorrectly also counts as being wrong. So please double check that. Yeah. Let's do some problems that are a little more complicated. So where we have to simplify. Let's say you have a, b to the negative 3, c to the negative 2, over a to the negative 3, b to the negative 4, c to the positive 6, all of that to the negative 7. Boy, that's a big problem. Essentially, there are two ways to go about this. We can simplify what is inside of the parentheses first and keep the negative 7 out, waiting while we simplify this, and then apply the negative 7 after. Or you can apply the negative 7 first and then simplify what is left over after we simplify that. Let me show you both ways. I don't think one is necessarily better than the other. Okay, so let's say you are given this problem to simplify. So I'm going to start by simplifying what is inside of the parentheses. This is a negative exponent, so that goes up here. This a has a hidden exponent of 1. So we have 3 a's and 1 a here. That makes a to the 4. A to the 4. Whoa, this one's supposed to go up here. This one is supposed to go down as we make those exponents positive. Sure, we could do that. So we got, because of this denominator, or because of this factor, we got 4b's on the numerator as we move that to the top. That goes down to change that negative into positive. And then we have 3 in the bottom. So 4b's on top, 3b's on the bottom. That means that there's going to be only 1b left on the numerator. And then this guy has a negative exponent, so we have to move that to the denominator. And this one stays where it is because this is not negative. So it stays where it is. There's no need to move that. The reason why we moved that one is because that was negative. That had a negative exponent. This one doesn't have a negative exponent. So we add, or we multiply to this 6 c's, 2 more c's. So now we got 8 c's altogether on the denominator. I guess I didn't need to have that much room, but that's okay. Now, once we are at this stage, this is simplified. There's, again, 2 ways to do this. You can multiply the negative 7 onto those exponents. And then, again, fix the negatives because we're going to end up with negative exponents. All of them are going to be negative, actually, and then fix that by turning everything upside down. Let me do that. So when we multiply the negative 7 with this exponent, we end up with a to the negative 28. There's a hidden 1 here. 1 times negative 7 is b to the negative 7 over, and then a times negative 7, c to the negative 56. Okay. Now, all of them are negative, so all of them change where they are. So the c to the 56 stays in the numerator. Sometimes my 5s look a little funny. Sorry about that. A to the 28, and then b to the 7. And that is the simplified form of this. That's one way to go about it. Let me do it again. So problem number 10, again, differently. Yep. So we have, I'm copying this down again, a, b to the negative 3, c to the negative 2, over a to the negative 3, b to the negative 4, c to the 6. All of that to the negative 7. And we want to simplify that. This time, we're going to distribute the negative 7 first on top of all of the exponents. So we will have a to the negative 7. There's a hidden 1 here, multiplied by negative 7. And by the way, I'm assuming you already reviewed a little bit the properties of exponents. I don't want to write down all of those properties on this video because if you open just about any algebra book, they will have properties of exponents. Multiply those exponents because that's what the properties say when we have a product and we have an exponent outside of the product, then we can distribute the exponent. So we have b to the positive 21, and then c to the positive 14, over, multiply again the exponents, a to the negative, actually, that would be positive 21, because negative and negative makes a positive. 2 negatives again make a positive in this case. So b to the positive 28, and c to the negative 42. Okay, so we took care of the exponent outside, and now we simplify this. This one has a negative exponent, so it goes down. We already have 21 a's on the denominator. 7 additional a's are going to go down there, so now we're going to have a to the 28. Okay, now let's deal with the b's. There's 21 b's on the top, 28 b's on the bottom. If we simplify one by one, we end up with 7 b's on the denominator. And then we have 14 c's in the numerator. 42 are going to be added, well, multiplied with the 14 we already have. So that's going to make 56. 6. Let me compare to the previous answer. I was trying not to look on purpose, and sure enough, we got the same answer. C to the 56, A to the 28 in the denominator, B to the 7 in the denominator. Yep. Practice this. You want to build some muscle memory. You don't want to just see this once and then hope that it sticks. Yeah, let's do another example. 11. Say you have 49, A to the negative 3, B to the 0, C to the negative 7, all of that over 7, A to the 10, B to the 4, and C to the negative 10. All of that to the negative 2. Now, which method do you like better? One thing I like about this method is that it takes 2 steps, 1, 2, but you got to be very, very careful with the negatives. This method takes 1 extra step because we have to simplify, distribute the exponent. Oh, I guess just doing this, it's half a dozen, 6 or 6. Which one do you want to do? Let's simplify first the whole fraction. So 49 and 7 does simplify to 7 on the numerator. Okay, we got negative a's or reciprocal, so those move down. So we got a to the 13, 10 to start with and 3 more. Oh, in this case, we're going to assume that b is not 0. Assume b is not 0, and that is just 1. Since we're multiplying, 1 does not affect the product, so we can just ignore that. Again, this is 1 because we're assuming b is not equal to 0, and multiplying by 1 does not affect the product, so we can ignore this factor altogether. C to the negative 7, oh, keep this b down here, b to the 4, and then, oh, there's a flip-flop. So this c goes up here, 10 of them, that c goes down, 7 of them, so we got 10 on top, 7 in the bottom, that means we got 3 on top there. So sometimes when I do this with a pen, I make up more room than I need. All right. So now we gotta do this. Let me try to do this in one shot. So this 7 is gonna be squared and it is gonna go on the bottom, 49. This c to the 3 is gonna be squared and it's gonna go on the bottom. So that is c to the 6. Likewise, this guy is gonna be squared. Remember your properties of exponents. Multiply the exponents when we have an exponent on top of the other exponent. So that is going to be a to the 26, and then b to the 8. So that is our final answer. And there's about 2 or 3 different ways to do it. Now, one thing we have to notice is that the 49 squared is going to be a huge number which then we have to simplify later. So it may pay to simplify first. Yeah, now that I think about it, because 49 squared is going to be a big number which we did not have to deal with because we did not distribute the bigger x or this exponent first. Rather, we simplify, so we never had to square the 49. So I think this is a little better now that I think about it. Sometimes the factors are just look not very friendly, but don't be afraid of them. Example 12. So let's say you got x minus 7 to the negative 3 times x plus 5 to the negative 2 over x to the negative 2, x minus 7 squared, x plus 5 squared, and then x plus 1 cubed. So let's say we have this to simplify. Let's see, I think this can be done in one shot. So x squared, this has a negative exponent. This goes to the numerator. Now we got two of the same. This one is positive, stays in the bottom. This one has a negative exponent, goes down, adding or multiplying with the two we already have in the denominator. So we have 3 and 2 make 5. So x minus 7 exponent of 5. Just pretend this is a to the negative 3 and a squared. Same thing as we were doing in the other examples. Same thing here. This goes on the denominator. So we have x plus 5 to the 4 because we have 2 in the denominator to start with, and then 2 more that have to multiply with those in the denominator. And then this guy stays where it is, x plus 1 cubed. So there it is. That's the answer, except we want to write it a little nicer. So we have x minus 7 to the 5, x plus 5 to the 4. We usually want to keep our elements centered, so we typically put the x squared in the center, and that's it. So this integer exponent portion is not too bad. Just take your time as we work out these problems, because it's easy to make mistakes. But that's the whole point. We have to pay attention to the details of those expressions. All right, with this, we will stop this video.